Okay, so here we are. I don't know how well this will show up on camera, but I've made a little program in Mathematica here. So we're going to go for I equals 1, I less than t. T is this gigantic number. I don't even know how big it is. I just wanted it to stop at some point, and I wanted to do a for loop so the code wasn't too hard to explain. And so we start at our number. Am I high enough to show what A is on there?
Yeah.
So in this case, we were looking at 4, but I'll make it be 3. So we're going to try to go up to 3. And so if A minus 1 over I, so 1 over the number, the starting number of the count, is bigger than 0, I subtract that away, and I print that number, I.
Yeah.
And then I show what's left for A. Okay. And as long as A is greater than 0, I keep going. Until we stop.
Okay.
Okay. So, this part down here tells me where to go, how to increase I, and that's part of sort of part of what David Radcliffe explained initially when he posted this. But we'll see maybe as an example. It's easier to talk about that.
Okay.
Okay. So here's what happens when we try to find 3.
So it's,
Summing up to 3. Let me zoom
so
out just a
looks
little
like
bit.
a problem occurred.
Well, so 3. So first it's 1 over 1. That leaves me at 2.
Mm-hmm.
Okay, and there's 1 over 2. Then I go, so I can add a half.
Yeah.
That leaves me with 3 halves to go. Then I add a third. That leaves me with 7/6 to go. A fourth, plus a fifth, plus a sixth, plus a seventh, plus an eighth, plus a ninth, plus a 10th. And now when I have a 10th, this number looks like around 1 over 14. In fact, it's even a little smaller than 1 over 14 because its reciprocal of what I have left is slightly bigger than 14.
Yeah.
So that's what that strange code above was doing. So the next thing, I don't need to check if I can subtract away 1/11th because I know I can't.
Yeah.
So I jump to 1/15th and subtract away that. And now I'm left with 1 over slightly more than 229. So I check 1 over 230. And that leaves me with exactly 1 over 57,960 left.
So then you subtract that away.
So can you tell me from reading what's on the screen, how do I make 3 from reciprocals? What do I do?
You make it's 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth plus a ninth plus a 10th plus a 15th plus a 2/30th plus a 57,960th.
And that's the error that you see when there, what's left is 0, and then I try to print 1 over 0, and it tells me there's an error.
Right. It tells you that you can't print 1 over 0.
I can't print 1 over 0. So it's actually pretty neat. So Dave Radcliffe gave an exact procedure for doing this, and the thing in his proof that he noticed that's actually really neat. And I'm not going to go into the proof about why you can do this for all rational numbers, but what's neat about it is Dave noticed that once you start jumping up in numbers from 10 to 15 to 230 to 570, or 57,960,
Not 570.
Not 570. The numerators of your complicated fractions actually start going down, 179 to 11 to 1.
Huh.
And so the numerators are always getting smaller once you start jumping.
Cool.
And that means the most I could have after a 10th, once I start jumping, the most I could have is 179 more terms. Because it's always getting smaller after that.
Yeah.
And in fact, I have much fewer than 179 terms because it goes 179 to 11 to 1.
Yeah.
Okay, so I want you to pick a reasonably small, don't go bigger than 3, but pick some rational number. We'll go back up to the top. And we'll pick some rational number. What's a rational number less than 3? But a fraction that's not an integer.
How about 3 halves?
3 halves. Okay. Well, that one's going to be easy. You can even do that one in your head.
Yep.
What's that going to be?
1 plus a half.
Yep. Okay. So give me one that's more complicated.
14 over 27.
14 over 27. Okay. Can't be simplified.
Yeah.
So let's see what happens here. when I go down, sorry for moving the camera. I moved too far down. There it is. What does it say?
1 is 1/2 and then 1/54.
Yeah. 1/2 plus a 54. So that one ends up being not too hard at all. Pretty cool. All right. Why don't you pick one?
All right. How about 2 and 13/19?
2 and 13/19.
Yep.
You know what? I don't know if how Mathematica wants me to do 13/19. So what's 2 times 19
38.
plus 13?
That's gonna be 51. So
51/19. Okay, great example. All right, so let's go down.
Whoa. So we have this.
Okay, read out what 51/19 is.
So wait, how do I read this? It's 1
Yeah.
plus a half,
Yep.
plus a third, plus a fourth, plus a fifth, plus a sixth, plus a seventh, plus an 11th, plus 1 over 2251, plus 1 over
What is 2251 as a number?
2,251,
Okay, good.
and plus 1 over 21,954,754,
Okay.
plus this.
What is that number?
Over, let's see, 1,000 billion, 723 quadrillion, 16 billion, 812 million,
Wait. You started at quadrillion.
Yeah, this is 723 trillion,
Yep.
16 billion,
Mm-hmm.
812 million, 846,020.
Yeah. So, okay,
Jeez.
so that's awesome. So 51/19 turns out to be much more complicated than 3,
Yep.
Yes.
which is pretty amazing, actually.
Yeah.
Okay, so we're going to break and we're going to go look at 4 now.
Okay.